All right, guys, let's start. So we are doing now your very interesting topic, right? We are getting into your probability and statistics, right? Very, very interesting. We're trying to understand today introduction to probability, right? The first chapter. Uh, Anybody who's trying to understand quant finance or finance in general, right? You cannot master finance unless you understand probability and statistics well, right? So this is our first chapter. We'll try to understand this. Fundamental of probability is the name of chapter. We are doing the introduction, so small chapter introduction to probability. Uh, Again, right, it is actually one of the most important chapters in all of your quant finance. Why? Because every major model in finance is ultimately a probability model. Black-Scholes probability of future stock prices, Monte Carlo simulation probability of future scenarios, war, value at risk probability of losses, credit risk probability of default, machine learning probability of outcomes, Bayesian model probability updated by information. You can think of probability as the language used by finance to talk about your uncertainty. Without probability, quant finance does not exist, right? So we need to understand that. Okay, let's dig deeper, guys. Let's try to understand more. Okay, now we are getting into your next part, which is the understanding of probability, where we're talking about probability framework for quantifying your uncertainty. Okay, the slide says that probability is the mathematical tool used to model your uncertainty. This is the single most important idea, right? Uh, when we try to understand your statistics, right? What we try to do, right? In very, very simple way, in deterministic mathematics, we have your 1, 2, 3, 4 values, right? There is no uncertainty, but finance is uncertain. Tomorrow's stock price is not fixed, right? Instead, we have many outcomes, right? Many outcomes are possible. Probability tells us how likely each outcome is. And why does finance needs probability? Because if you look at the slide, right? The slide mentioned risk measurement. Example, war, expected shortfall. Suppose portfolio can lose, your losses can be your 0 or 5 million or 20 million. 0, the probability might be 80%, 5 million, 15%, 20 million, 5%. Probability, let us quantify risk. Without probability, no war, no stress testing, no capital regulation, no Basel regulation. So we don't know, right, how to measure risk without probability, right? Similarly, about portfolio decisions, right? Uh, if you have to understand which asset is better, asset A or asset B, with different returns, different risk, we need probability distribution of returns, not just your average return. This becomes a modern portfolio theory. Similarly, for derivative pricing also, right? We need to understand option pricing asks what is probability of stock ending above the strike. We have to do it for call or put. We know the formulas. The future stock price is random, therefore option pricing is fundamentally your probability pricing, right? For sample space, please understand we have sample space, which is about set of all possible outcomes, right? Which is given. Even any subset of sample space, which is given, probability on event is this. Axiom total probability of sample space is equal to 1, right? So what does it mean? Basically, sample space is the universe, everything that can happen, right? Nothing outside this set can occur, right? Uh, More interesting part is that sample space can be continuous also. This is where quant finance start becoming sophisticated. Okay. An event is a simply a subset of outcome. Think of your sample space is equal to entire universe, even something you care about, right? And in finance, sample space is all about your all possible stock returns. Your event could be your stock which is generating a positive return, right? And probability of event, the slide gives you that it falls between 0 and 1, that we know. Everything lies in between. This is the first probability axiom which you see on screen, which is probability of S is equal to 1. Total probability must equal your 100%, right? Very, very important to understand. Please keep that in mind, right? Okay. Whenever you're studying probability, you have to be very clear about understanding all these things, because if you don't understand the basics well, right? If you don't understand the basics well, then it is very difficult to kind of go and understand the advanced concept, right? So you have to kind of understand the key takeaways, right? Key takeaways very, very well. And once you do that, I think you'll be totally fine, right? So keep that in mind when you're practicing, when you're understanding, keep in mind what is sample space, what is the event, what is the probability of event, the total probability of the sample space. Very, very, very important to understand when you are trying to kind of master it. Okay. All right. With this, we move into the next part, right, where we have to understand your probability on event, right? We have been given a formula. We have a particular example, right? When you talk about your probability definition, right? Here we are talking about your equally likely outcomes, right? For equally likely outcome, probability of E is equal to what? What's the numerator here? The numerator is number of favorable outcomes, right? And S is the total outcomes, right? So, for example, let's say take a die example, right? Sample space in a die is your what? 1, 2, 3, 4, 5, 6, right? I don't need to write it, but okay. Okay. So event is your 5, 6. Count outcomes S equal to 6. Event is equal to 2. Therefore, probability of E by 6, 2 by 6 equal to 1 by 3, which is 33.3%. Finance connection here, this formula works only for equally likely outcomes. In finance, outcomes are rarely equally likely. For example, returns might be 10%, probability is 5%, return might be 0, probability 60%, plus 10, 35%. Now simple counting breaks. We move to probability distribution, normal distribution, log normal distribution, Poisson distribution, later stochastic process. We need to understand all those, right? So keep that in mind. Next one is about understanding simple event versus your compound event. What's a simple event? See, simple event contains exactly one outcome. Example, E is equal to 3, right? Only one possibility, probability of E is equal to 1 by 6 because it's only for 3. Compound event contains a multiple outcome. For example, F246, probability of F is equal to 3 by 6 equal to 1 by 2. Finance interpretation here is simple event ST is equal to 100, stock ends exactly as 100, compound effect ST is greater than 100, stock ends anywhere above 100. This is much more realistic. Most finance questions involve compound events. For example, probability default occurs, probability stock rises, probability loss exceeds your war. All compound events we need to understand very, very clearly. Okay, then we have your complementary events. This concept appears everywhere in risk management. If E is equal to event, then complement EC. EC means event does not happen. Formula is PE plus EC is equal to 1. Therefore, PEC is equal to 1 minus PE. For example, P is equal to default, then probability of no default is equal to 98%. Use complement rule. Quant finance uses credit risk, very, very common. Instead of calculating probability of survivors, directly we often compute probability of default and use probability of survival equal to 1 minus probability of default, which is very, very important. Okay, so keep that in mind. Simple calculation, basic part. Then we get into mutually exclusive events, which is a disjoint events, right? Okay. So again, events cannot happen together here. Formula A intersection B, right? They don't have anything, right? What is happening here? What we are saying is, for example, right? Let's just do it by example, right? Die roll, A is 2, B is 4, cannot occur simultaneously. So union rule for mutually exclusive events, right? P A union B is equal to P A plus B, right? Finance example, for example, A is stock returns greater than 10%, B stock return less than 10%, or let's say less than minus 10%. On the same day, both cannot occur, right? Therefore, mutually exclusive, right? I hope there is no overlap between the events. Okay. With this, we get into the next slide, which is independent events, right? So independent events, the slide is extremely important. Most of the quant finance is built on independent assumption. Occurrence of one event does not affect the other, right? So probability of A kind of, right? Probability of A and B, right? A and B is equal to probability of A into B. Probability of A conditional on B is equal to probability of A. Probability of B conditional A is equal to probability of B, meaning learning B occur tells us nothing about A. Example, PH is equal to 1 by 2, die P6 is equal to 1 by 6. You know, therefore, right, you are just multiplying it. 1 by 2 into 1 by 6 will 1 by 12. The huge quant insight here is that many models assume returns are independent, but in reality, returns often show kind of your dependence. Volatility clustering, market contagion, credit contagion, correlation, popular. This entire field exists because independence often fails, right? So very, very important. Independence means no probability influence, even if both can happen together. Very simple, very straightforward. Till now, we are doing high school stuff, guys. Now, quick summary, event types and key rules. Critical distinction, mutually exclusive, uh, cannot happen together. A kind of A and B has nothing in common, null. Independent can happen together, but neither affect probability of other, right? So in independent, uh, we should be very clear that this is what we're looking at. Shouldn't confuse these constantly. Uh, Independent can happen together, but neither affects probability of the other. Keep that in mind. In fact, for non-zero probabilities, very, very important to understand, right? Mutually exclusive events are never independent. Why? If A happens, B becomes impossible. Therefore, probabilities are affected, hence dependence exists. Very, very important to understand. Understand the complement, compound, and simple. Key message, mutually exclusive events are about no overlap in your outcomes, while independent events are about no impact on your probabilities. Then we get into the next part, which is conditional probability, probability updates with information. This is where probability becomes very truly special. From we're talking about P, probability of A, conditional event B, probability of A and B divided by probability of B, meaning we first observe B, then update our beliefs about A. Think before information, probability of A, after information, probability of A, dependent on B. This is learning, this is the foundation of Bayesian thinking. In the quant finance interpretation, before earnings, probability of stock rises, after strong earnings, probability of stock rises, divided by good earnings, probability changes, information changes, beliefs, which we need to understand very, very clearly. Okay. So this is what we keep in mind. Key takeaway, conditional probability is the foundation for learning from data and updating beliefs in finance, which we need to know very, very well, right? Then we go into the next part. Again, finance example, excellent example, stock up, given market up. We define A is equal to stock rises, B is equal to market rises, then P, A by B is equal to P A intersection B divided by PB. Interpretation is if P A by B, E conditional B is greater than P A, right? What does it mean? The stock tends to move with the market, positive market sensitivity, high beta-like behavior. If it is this, P A conditional B is less than P A, less sensitive to market rally. Why this matters in quant finance? Because everything data comes from this idea. Your conditional probability leads to your Bayes theorem, to joint distribution, to correlation, to multivariate normal models, copulas, your credit portfolio models, your Monte Carlo simulations, your machine learning, your modern quantitative finance. So these first 10 slides are not your elementary probability. These are actually laying the mathematical foundations for everything you data study in your derivative pricing, risk management, portfolio theory, your credit risk, stochastic calculus, and your quantitative trading. Okay, keep that in mind. Okay, now we get into the next part, which is about Bayes theorem, right? Bayes theorem, we are talking about the updating probabilities using new evidence. This is one of the most important formulas in modern quantitative finance, machine learning, A and risk management. The slide gives you the formula, right, which is here. Uh, Again, as a student, please understand, we don't need to memorize it. They can't understand why it exists. The big idea is, suppose before seeing any information, you believe something, right? Then new information arrives. You observe the event. Now your belief should change. Base tells you exactly how much, and there are components which you should be well aware when you're studying your Bayes theorem. Very, very important to understand. Uh, Again, see, Bayes theorem is an extension of your conditional probability, right? So when you are studying Bayes theorem, right, make sure that you keep in mind uh, how exactly your conditional probability was understood earlier, right? See, earlier conditional probability was given in very simple terms that PA dependent on B is equal to P A intersection B divided by your PB, right? Now, what I'm trying to put across is that as we go ahead, right, as we go ahead, we realized uh, that sometimes when I have to find P A by B, A condition on B, that is not easy to find, right? So I have to, and the opposite is easy to find. What is the opposite? P B by A. The opposite is quite easy to find, right? So this formula of P A by B, where we are talking about P A by B is equal to P B by A. So you're talking about P A by B is equal to P B by A, right? So you're talking in other way around, right? So the whole idea of this formula is that sometimes you just can't get something very quickly. In that case, what is important to understand is that you might have to change your beliefs, right? So see, P A by B is the posterior updated belief. PB by A is the likelihood evidence under A. PA is the prior belief before evidence. PB is the marginal likelihood overall probability of defense. The final relevance here is updating default probabilities from new trade signals. It is used. Updating regime probability after macro levels. It's used. Bayesian volatility forecasting risk models. There it is used. Bayes theorem is the mathematical rule for learning from information in real time. Right? Keep that in mind very, very clearly. See, when you are trying to see these kind of formulas, right? What is important to understand is that these formulas have been created to make your math simple, right? So somebody has worked on it and has created this formula because ultimate point was that how do I make calculating your condition probability much more easier, right? Because calculating A by B was quite difficult, right? And we found a hack. We found a hack that can we calculate A by B using B by A. So that is what has been given here for all PB greater than 0, right? So please understand why Bayes exists, right? Bayes exists because you start from conditional probability, you rearrange, you substitute. Bayes theorem is simply your conditional probability rewritten, nothing magical. Finance examples which have been given, your default rate, suppose prior default probability is known. Now rating agency downgrades the company. Historically, the formula Bayes lets you update that. This is exactly what banks do. The quantitative insight here is that a huge amount of quant finance is prior belief plus new information, updated belief. Example, your credit models, your Bayesian volatility models, your regime switching models, your market forecasting, machine learning, signal processing, all are Bayes in disguise. So you understand that. Okay. Then we get into slide number 12, right? Additional rule probability of A or B, right? So now we move to unions. The question being, what is probability of A or B happening? The formula is given here. Why subtract the interaction? Because the A plus B counts outcomes in A and B twice, A intersection B twice. We subtract once, mutually exclusive one, A intersection B is null, then this is what we get. Key takeaway, union probability depends on overlap between events, intersection. Very, very important. Okay. So that is what we get. Outcomes belonging to both A and B are counted twice, therefore subtract overlap once. You need to keep that in mind, right? Very simple. From the quant finance perspective, suppose you have A as stock rises, B as bond rises, someday both rise, therefore that is your intersection, right? And you need to have full formula to understand this. That is very, very important. Okay. Then we get into your slide number 13, right? Rolling a two or fair on a fair die. Again, the consider fair six-set die, sample space is given, define events A and B, A intersection B null, this is 0. If you're using the mutually exclusive addition rule, we get this. You can calculate the numbers. For mutually exclusive events, probability of A or B is just the sum of the probabilities, right? This is also not difficult. Again, why this matters in finance? Because many risk events are mutually exclusive. For example, daily return greater than 10% and return less than minus 10%, therefore cannot occur simultaneously. Therefore, probabilities simply add, which we need to understand, right? Then we get into question number 14, multiplication rule. Calculate the probability that two events occur together, right? Very, very interesting. Equivalent form is also given. It's just rearranging of formulas. We are talking about what is probability of both events happening together. Intuition is think sequentially. Step one, given A occurs, probability of A. Step two, given A happened, B occurs, probability of B by A, B dependent on A, probability of B dependent on A. Multiply them by multiplication. Imagine probability of rain tomorrow 30%. If rain occurs, probability of percent. Therefore, probability of rain intersection with traffic 0.3 into 0.8 is equal to 0.24, 24%. From the quant finance perspective, suppose A is recession, B is stock market crash. Probability of A intersection B is equal to probability A into probability of B dependent on A, conditional on A. This appears everywhere in your stress testing, which we need to understand. So probability of both happening depends on how likely the second event is after the first event occurs. Okay. Then we get into question number 15. We talk about independent events, which is a simplified mathematical rule. Two events are independent. If one event does not affect the other, this is what we have. Independent multiplication rule. This is what we have. And this is the example. When events are independent, joint probability is the product of the individual probability, right? So no influence substitute into multiplicative rules. P A intersection B is equal to probability of A into probability of B. Example, coin, probability of heads is equal to 1 by 2. Can be a die also, probability of any number 6, let's say 1 by 6. Probability of head and a die giving you 6 is 1 by 2 into 1 by 6, which is 1 by 12. Why quants love this formula? Because many models assume independence because it simplifies everything. Probability of A intersection B is equal to probability of A into probability of B conditional on A. Now you get probability of A intersection B is equal to probability of A into probability of B, right? So much easier now we are getting. The problem is reality is rarely independent. Financial crisis teaches repeatedly. 2008 example, before crisis, mortgage default assumed almost independent. Reality, housing price fell, everyone defaulted together, dependence exploded, models failed. So we need to keep in mind that reality is seldom independent. Then we get into dependent events, your conditional multiplication rule. Now we remove independence, right? Where we're getting to the formula which we have discussed earlier also. Still holds, but now keep in mind the probability B by is not equal to probability of B, right? Why? Because see, since the first draw changes the deck, events are dependent, right? A is the first card is an ace, B is the second card is an ace after an ace was drawn, right? So in card example, first card ace, second card ace, without replacement. After first ace is removed, deck change, probability change, therefore dependent. You look at the financial example, very, very important to understand. A is recession, B is corporate default, probability of default. By recession, probability is greater than probability of default. Huge dependence, this is actually by credit risk model exists. The deep quant insight here is most advanced quantitative models is actually about dependence. Example, correlation, copulas, great portfolio models, systematic risk, multi-factor models, all try to answer how the occurrence of one event affect another. Okay. Then we get into your slide number 17. Your option pricing, again, here now probability start becoming finance. We are looking at call payoffs or option payoffs. Example given is European call payoff. This is the formula which we know. Interpretation if stock finishes above strike, positive payoff, otherwise zero. Example, let's say K is equal to 100, stock is equal to 120, payoff is 20. If stock is equal to 80, payoff is zero. Why probability matters? Because we don't know future stock price. ST is kind of random, therefore pays random. So option price equal expected future payoff discounted today. We have risk neutral pricing also given. C naught is equal to minus exponential RT EQ max of ST minus K, 0. This formula is one of the pillars of quantitative finance. We need to understand every symbol here. Exponential minus RT is the discount factor. EQ here is the expectation under your risk neutral measure. Max of ST minus K, 0 is the random payoff, which we need to understand. Then we go to Black-Scholes assumptions, which is DST is equal to R minus QST DT. Sigma STDWT. This says stocks evolves randomly, where R is the risk-free rate, Q is the dividend yield, sigma is the volatility. DWT is the Brownian motion or the random shock. Key quantitative insight is option pricing is not really about stock, it is about probability distributions. The option price changes because of probability distribution changing, right? So that's what we need to look at. Okay. Then we get into your slide number 18, risk management and your portfolio optimization. Again, application 2. Slide connects probability to portfolio management. VAR, the slide gives you probability of loss is greater than VAR 1 minus alpha. Example, 95% VAR. Alpha is equal to 95%, then probability of loss greater than or is 5%, meaning only 5% scenarios are worse. Expected return, portfolio weight W, expected return mu, portfolio return ERP is equal to WT mu. Example, two assets we can take. Let's say we are taking W is equal to 0.6, 0.4, and we take mu. Mu is equal to 10%, 5%. So if that is the case, right, expected return of the portfolio is equal to 0.6 into 10, 0.4 into 5 is equal to 8%. Portfolio risk here is VAR of your return of the portfolio is equal to your WT. And what is happening here? Please understand this is your covariance matrix, right? This is one of the most important formulas in your portfolio theory. The formula captures the volatility, correlation, diversification all together. The deep quant insight here is that expected return uses mu, risk uses your covariance matrix, right? Modern portfolio theory is basically optimize expected return while controlling your variance. Okay. So probability connects uncertainty to real decision, risk limits, optimal weights, and your hedging strategies. Okay. So keep that in mind. Then we get into the next part, which is key takeaways from probability concept. The slide summarizes the journey. We understood the events, then we understood the conditional probability, right? Very, very well. Then it moved to Bayes theorem, right? And that leads to decision making and quant finance, right? So very simple. It's a repetition. Why this matter? Because accurate probabilistic thinking improves modeling and decision making. It is the foundation of most quant finance models or methods. Finally, what probability pars? Probability in quant finance, what it pars is the most important summary slide. Probability underpins your C naught is equal to minus exponential minus RT, EQ payoff, risk management, VAR, expected shortfalls, stress testing, scenario analysis. Portfolio optimization is given ERP is equal to your this value, VAR is equal to this value. Again, please understand these all formulas we have already understood, right? How they have been calculated. Dependence modeling, A intersection B, A union B, later becomes correlation, covariance, copula, multivariate distributions. Probability connects uncertainty to measurable risk and optimal financial decisions, which we need to understand. Okay. Everything you have learned in slides till now, right, is all about how we move from probability to conditional probability to Bayes theorem to random variables to probability distribution to expectations and variance, multivariate distribution. Then we go to stochastic processes, then Black-Scholes, then we'll go to Monte Carlo, then credit risk model, then machine learning, the modern quant finance. The entire understanding of probability here looks very elementary, but conceptually it is the foundation upon which virtually every advanced quant model is built. Okay. With that, we get into the questions. Pretty straightforward question, right? If a fair die is rolled once, find the probability of getting an even number, right? So very, very simple. See, if the fair die is rolled once, right? How do we find the probability of getting an even number, right? It's simply, right? You take the sample space, you take the kind of expected your, what you say, events, right? So sample events divided by your sample space, right? If you do that, right, you will be totally fine, right? So if you take fair dice rolled once, right, event outcomes is 2, 4, 6. Total outcomes is 6, right? So probability of even is 3 by 6 is 1 by 2. Very straightforward, right? I think this is high school question, right? Not even quant finance, right? A card is drawn from a standard pack. What is the probability the card is king, given that it's a face card? Again, how many face cards are there? If you take face cards, paid cards, your J, Q, K, 12. Again, kings out of that. How many kings are there? 4. The probability of K for the face cards equal to 4 by 12 equal to 1 by 3. Very simple, very straightforward, right? Then we get into question number 3. EX with outcome of fair die, compute expected value of X. Again, expected value of X has to be calculated in a particular way. There is a formula, basically what we do. It is 1 into 1 by 6 2 into 1 by 6, 3 into 1 by 6, 4 into 1 by 6, 5 into 1 by 6, 6 into 1 by 6. What you do is you take 6 common. 1 plus 2 plus 3 plus 4 plus 5 plus 6. Right? So this becomes 21 by 6 is equal to, yeah, 3.5. See, when you're trying to find the expected value, right, you have to be clear. You are taking what? You are taking that particular number, that particular 1, 2, 3, 4, 5, 6, which can occur, right? And then you are multiplying that, right? Then you are multiplying that with probability of that event happening, right? 1 into 1 by 6. That's why 2 into 1 by 6, 3 into 1 by 6, plus 4 into 1 by 6, plus 5 into 1 by 6, plus 6 into 1 by 6. Okay. So this is what we have. Okay. Quickly. Then next one is X be a Bernoulli random variable. Probability of X is 0.3. Compute your variance of X. Again, please understand variance of X in your Bernoulli distribution is given by a formula P1 minus P, right, which is 0.3 into 0.7. You have to remember the distributions and their formulas, guys. So it's 0.21. It's a Bernoulli is a type of distribution. Its formula is P into 1 minus P. So if you remember it, you can easily solve it, right? So that should not be an issue, right? Question number 5, the disease affects 1% of population. So probability of disease is given as your 0.01, right? So probability of not having disease, right? So D dash, let's say 0.99. Then a test detects the disease correctly with probability of 0.9, right? So probability of your test, right, for disease is 0.9. Okay. And probability of test for disease kind of false probability, right? Gives a false positive, right? So is equal to your 0.05. Now, if I have to find the probability that a person has a disease given a positive. So see probability of disease, the question asks you, question, see, this is what I was telling you when I was teaching you in the notes, I was teaching you Bayes theorem, right? See what the question is asking. The question is asking probability of your D, right? Probability of D, okay? Conditional on somebody having a positive test. So this will become probability. So D by T, nowhere it is D by T, right? Everywhere T by D, T by DC, right? So probability of T by D into probability of D, right? And divided by probability of T, right? So this becomes very interesting, right? Because what has happened is that we have converted, right? We have converted something which we did not have, right, to something which we have, right? So this is where the Bayes theorem plays very interesting role. So if you put the formulas now, right, what is the probability of T now? And if somebody has to find probability of T now, probability of T has to be found by a joint probability formula, which will be you multiplied 0.9 into 0.01, right, and your 0.05 into your 0.99. This is joint probability formula. Get joint probability. Joint probability. How do you find the joint probability, right? So we are taking 0.9 into something happening 0.01, right? So 0.9 into 0.01 and 0.05 into 0.99, right? So this is coming as 0.0585. So finding denominator is very challenging here, to be fair. 0.585, right? And then this is easy, right? This is easy because what is happening here? T dependent on D is 0.9 and D is given already 0.01, right? You solve it, you get 0.154. That's it, guys. That's the answer. Okay. This is the only mildly difficult question in this chapter, right? Otherwise, everything is repetition, right? All the solutions are already given here. I've solved it, but all are already given, so you can go back and see it. That's it, guys. That's what we were supposed to do. We have completed this chapter. I'll see you in the next chapter. Go back, revise it. It's not very difficult here. This is very easy kind of chapter. This is only covered because we want you to revise what was taught in high school or your early college days. Nothing difficult. I think very basic, right? Even people who are appearing for, let's say, competitive exams, even NEET medical exams or your IIT JEE or any engineering exams, they already know this, right? So this is it's not exactly a quant finance. This is school kind of thing. Only thing I've given here is that I've tried to join the concept with why we are studying it, where it is related, how it shapes up the future, calculations, etc. Right? So that's what I've done. Otherwise, pretty straightforward, pretty simple, right? And how this whole thing chapter relates to quant finance, that was my duty. I've done that. Otherwise, simple. Go back, revise it twice. You will be fine. Okay. That's it, guys. I'll finish. I'll see you in the next lecture. Okay. Thank you.